Now we're going to talk about the buoyant force. So the buoyant force is going to be what pushes up on you and makes something feel lighter. So it could push up on you or on an object. So for example, here we have a weight. And when it is just hanging from the scale, it is registered as weighing 7 newtons. And when you put it into the liquid, all of a sudden, it only weighs 4 newtons. Now, what's really interesting about this is that means that the buoyant force is 3 newtons. So somehow when we have our force diagram, we're going to have the buoyant force pushing up on it. We have this tension pulling up on it. And we have the gravitational force pulling down on it. And what's really interesting is that if you weigh the water that would spill out, so whatever the volume of this mass is, whatever that water is, it goes in here and you weigh that water, it is also 3 newtons. So these two things are going to be the same. The weight of the water that would get displaced and the buoyant force are going to be the same. Now, when this is in the water, the other thing that you need to know is what this is called. When it is in the water, this tension is called the apparent weight. And if this block was sitting on the bottom of the beaker and there was a normal force pushing up on it, then that would be the apparent weight. And when it is out of the water, the 7 newtons is also the apparent weight. So when it's out of the water, this apparent weight and the gravitational force are going to be equal because there's only 2 forces and it's not accelerating. But when it's in the water, your apparent weight is just the Ft. And the last thing to recognize with this is when you're talking about the buoyant force here, we can figure out that buoyant force by finding the gravitational force of the water displaced. And the way you can figure that out is if you have the mass of the water. And the way that you're going to do this is to find the mass of the water. You need to find the volume of the water displaced and use the density of the water. So all of these all have to be the same thing. We're talking about the density of the water, the volume of the water, and the mass of the water. And specifically, it's not all of it, it's the amount that is displaced. And so once we have this mass of the water displaced from this, then that can be used to find the buoyant force because we know the mass of the water displaced times g is equal to the gravitational force of the water displaced, and that is equal to your buoyant force. So if you know the volume, then you can find the mass of the water displaced. So you can find the gravitational force of the water that is displaced, and this is equal to the buoyant force. Archimedes. So Archimedes is chilling in his tub when he realizes that he appears to weigh less than usual because of the buoyant force. He is so excited, he yells Eureka, and as legend would have it, he immediately jumped up and ran into the streets of Greece to share his discovery. If Archimedes has a mass of 85 kilograms, a volume of 0.063 meters cubed, and is only half submerged in the tub, what is the buoyant force of the soggy Greek man feels due to the water? And find the normal force the tub exerts on him. All right, so the first thing that we need to do is we need to recognize that the volume of Archimedes, that the water displaced is only half that much because he is only half submerged. So that means the volume of water displaced is going to be whatever 0.063 divided by 2 is equal to. All right, so we have the mass of Archimedes and we have the volume of water. Well, the way that we're going to be able to find that buoyant force is if we know the volume of the water and then also the density of the water. But we don't know the mass of the water displaced, so we're going to have to find that first, and we're going to find that with density. So the density of water is 1,000 kilograms per meter cubed. And that's going to be equal to the mass of the water displaced divided by the volume of the water displaced, which is this 0.063 divided by 2. And I get 32.1 kilograms for the mass of the water displaced. And then I can take this and plug it in here to find the buoyant force, because then the buoyant force will be equal to the mass of the water displaced times g, and I get 314.58 newtons. All right, so let's draw a force diagram now. We've got this buoyant force of the water pushing up on Archimedes. And we can find the gravitational force on Archimedes, because that'll be the mass of Archimedes, which is 85 times 9.8. Our buoyant force we just found here. And now we will be able to solve for our normal force using a net force equation. So the sum of the forces in the y direction is our normal force going up plus the buoyant force going up minus the gravitational force of Archimedes going down. And I get 518.42 newtons for the normal force acting on Archimedes.